Okay, so today's lesson is on the types of organic reactions. Last lesson, we talked about all of the different organic families that comprise all the different organic compounds. And in this lesson, we can focus on the reactions that result in the formation of these compounds and and talk about some of their practical applications. So there's, in this lesson, I'll talk about a list of organic reactions that I have listed here: substitution, addition, elimination, oxidation, esterification, hydrolysis, and polymerization. And the goal of this lesson for you is to understand these different types of reactions, to be able to identify them, and to be able to predict and correctly name the types of products that come from these reactions. So there are different types of organic reactions, and based on what type of functional group a certain chemical has, that will predict or dictate rather what type of reactivity there is. And there are generally four broad reaction categories. There are the addition reactions, which occur whenever you have two reactants that add together to form a single new product with no atoms left over. And by that, I mean what I have here in this picture, that you have these two reactants. And as the name suggests, you are adding them together to give this product. And there is no second product. There's no other atoms left over. These types of reactions are addition reactions. Then you can also have elimination reactions. And they are, in a way, you can think of these as opposite of addition reactions, where atoms are removed from a molecule to form this double bond. And they occur when you have a single organic reactant that breaks up into two products, often with the removal of some sort of a small molecule, such as in this case, H2O, or if it's the opposite of this addition reaction, it might be HCl. So the addition and elimination reactions are essentially opposites of each other, reverses of reactions of each other. Then the third broad category of reactions are substitution reactions, which take place when you have two reactants that exchange parts to give two new products. For example, you might have these two reactants. You might have a methane molecule, CH4, plus chloride. And they switch parts. So the hydrogen and one of the chlorines switch, and you get two new products. You get chloromethane and hydrogen chloride. Then there's rearrangement types of reactions that take place when you have a single organic reactant that reorganizes its bonds to give a new isomeric product. For example, you might have a butene, one butene, and it may isomerize to give a 2-butene. It's still the same atoms, it's just a rearrangement. So it's an isomeric product. This is a rearrangement reaction. So let's talk a little bit more in detail about addition reactions. Addition reactions, as I mentioned, just involves the addition of one or more particles to an organic molecule. And these often occur with unsaturated hydrocarbons, such as alkenes and alkynes. So in addition reactions, you are adding molecules to another hydrocarbon that contains either double bonds, one or more, or triple bonds, one or more. So these are unsaturated hydrocarbons, alkenes and alkynes. Addition reactions come in four types: hydrogenation, halogenation, hydrohalogenation, and hydration. So these 4 types we will talk about in great detail in the next 4 slides so that you can understand what are these 4 different types of addition reaction and what are their products. So the first type, the hydrogenation reaction, and as the name suggests, it involves hydrogen. In this reaction, you have hydrogen gas, H2, added to an unsaturated hydrocarbon. So again, it's an unsaturated hydrocarbon, either an alkene or an alkyne, a double bond or a triple bond. In this case, it's a propene, 1, 2, 3. So it's a prop, and it has a double bond, ene, so propene molecule. And hydrogen gas is being added to it under high temperature and pressure. And it results in a new molecule of propane. These 2 hydrogen atoms become incorporated, added to the propene molecule, resulting in propane. So hydrogenation is a process that actually has a lot of benefits. It has a lot of utility in the food industry. When you hydrogenate oils, you get longer shelf life. They become easier to handle, easier to store, particularly because of their long shelf life. And overall, they cost less because they can last a very long time. And that's great for the food industry. However, for us, it's not very healthy to be consuming hydrogenated oils because they cause problems such as atherosclerosis and hardening of the arteries and cardiovascular disease. So hydrogenated oils are not very healthy for us, but they certainly have their application in the food industry to a certain extent. The other thing I want to touch upon here under this type of hydrogenation reaction, and looking ahead a few slides, we are going to be talking about oxidation and reduction reactions. And some of you may already know about oxidation and reduction reactions. Here in this case, the double bond here between the carbon-carbon double bond is hydrogenated here, as you can see. Hydrogen is added to these 2 carbons, and the double bond is broken, and you have 2 new hydrogens added here. This is also called a reduction. And reduction in organic chemistry refers to usually refers to the addition of hydrogen or a removal of oxygen from a molecule. And for most alkenes, hydrogenations, either palladium metal or platinum is used as the catalyst to drive these hydrogenation reactions for most alkenes. The next type of addition reaction, remember we said we have 4 types of addition reactions. The next type is the halogenation, so involving halogen atoms. So molecules such as bromine or chlorine are involved in these halogenation reactions. And here you have the addition of a halogen, bromine, chlorine, fluorine, to an unsaturated hydrocarbon. So a hydrocarbon molecule such as ethane that has a double bond, or if a molecule has triple bond, then you can add a bromine or a chlorine or a fluorine to it, and you can get a new compound. In this case, our ethane, a halogen molecule of bromine is added to this ethane, resulting in a new molecule of 1,2-dibromoethane. And you can see here, this is an ethane molecule. It has 2 bromines added to it, and they're added at carbon 1 and 2. So, and then there's 2 of them. So 1,2-dibromoethane, that's the name for this new molecule. And these types of reactions, these halogenation reactions, can also take place with aromatic hydrocarbons. For example, you might have cyclohexene here in this case, one double bond here. Instead of cyclohexane, because it has a double bond, it's cyclohexene. And when you add bromine to it, you get a molecule of 1,2-dibromocyclohexane, because that double bond is gone now. So it's no longer a hexene. Now it's a single bond hexane. Halogenation reactions are very useful in manufacturing. They're very common in manufacturing, but a big drawback of halogenation reactions is that they produce those molecules, chlorofluorocarbons. Chlorofluorocarbons, as many of you know, their common name is freons. And they were first developed many, many years ago in the 1930s. Then they were widely used, especially in cooling devices such as air conditioning units or as refrigeration units, because they are they're non-flammable, they are non-toxic, they're cheap, and they go through the evaporation condensation cycle that these cooling devices need and operate on very easily. However, these freons cause a depletion of the ozone layer, which is a crucial part of our atmosphere that absorbs UV, ultraviolet light. And to the extent that one molecule of freon is able to catalyze the destruction of 1,000 ozone molecules. So very, very destructive to the ozone layer. And so they're not so widely used. Not so widely used anymore. There's alternatives. The third type of addition reaction is called a hydrohalogenation reaction. So as you can see from the name, as it suggests, it's kind of a combination of the two other types of the reaction that we talked about, the hydrogenation and the halogenation. This is hydrohalogenation reaction, where you have a halogen atom combined with a hydrogen. And that's termed a hydrogen halide. And examples of hydrogen halides are molecules like hydrogen fluoride, hydrogen bromide, and hydrogen chloride. So these are all hydrogen halides because they have one hydrogen and a halide. Hydrogen and a halide. Bromine, hydrogen and a halide, chlorine. And hydrogen halides combine with unsaturated carbons, like we have in this example here, to produce alkyl halides. So here we have an example where you have an unsaturated hydrocarbon such as propene, and to that, you're adding a hydrogen halide. So whereas in the other two examples, we had the addition of just H2 for hydrogenation. In halogenation, we had the addition of a halogen, like Br2, Cl2, F2, so all of these halogen gases. In hydrohalogenation, you have a hydrogen halide being added, such as HBr, HF, HCl, hydrogen bromide, hydrogen fluoride, and hydrogen chloride, respectively. And these then produce alkyl halides, such as bromopropane. But the question is, so the double bond is right here between these two carbons. Where is the H going to go? On which carbon is the hydrogen going to go on? And which carbon is going to take the bromine? Which one? It could be either this type of molecule, or it could be this type of molecule. So in hydrohalogenation reactions can also occur with cyclohexanes, with cyclohexenes, so cyclic aromatic hydrocarbons. And again, HBr is added to where the double bond is. One of them gets the hydrogen, one of them gets the bromine, and you get bromocyclohexane. Okay, so then this question of which one are we going to get? Anybody have any idea as to which molecule will be the molecule that we will get? Well, it's a good question, and we will talk about this further in the lesson. So just keep in mind that it can be either one of these, but only one of them will be the product of this hydrohalogenation reaction. And we will come to that. So the fourth type of addition reaction is a hydration reaction. So whereas just as you had hydrogen chloride or hydrogen bromide adding to alkenes to give alkyl halides, you could have H2O added to alkenes to give alcohols in a process called hydration. In hydration reaction, water, a molecule of water, reacts with a unsaturated hydrocarbon, again, the propene here as an example, and it will produce an alcohol. So here you will, the carbon-carbon double bond will be broken, and one of the hydrogens will go to one of the carbons, and the OH will go to the other carbon, giving you an alcohol. But again, the question is, does H go to this carbon and OH to this one? Or does OH go to this one and H go to that one? Which one? Do we get 2 propanol or do we get 1 propanol? Which compound is the product of this reaction? Which one? So as it turns out, there is a rule that can help us arrive at the answer as to which one of these products in a hydrohalogenation reaction and which one of these products in a hydration reaction we are going to arrive at. And that is known as Markovnikov's rule. And in Markovnikov's rule, when you have molecules of non-identical atoms added to a double bond, so as is the case here, where you have a hydrogen and a bromide, they're not identical. They're not, both of them are not hydrogen, both of them are not bromine. There's one hydrogen, one bromine, so unidentical. Or in this case, it's water. One of them is an H, one of them is an OH that is being added to the double bond. So when you have molecules of non-identical atoms being added to a double bond, then you get 2 different products that are theoretically possible, as we explored on the other slides. So for example, if you have hydrogen bromide added to the propene, you can get either one of these 2 products that are possible. So to answer which one, an experiment show that only one product is actually formed, and that product is this one with the 2-bromopropane, not the 1-bromopropane. So the bromine ends up going to this carbon and not this one. So this one would be wrong. This is the correct reactant from this reaction, the correct product from this reaction. So in Markovnikov's rule, says that when a hydrogen halide, as is the case with this molecule here, or water, H2O, is added to an alkene, double bond, or alkyne, might have a triple bond, then the hydrogen atom goes to the carbon atom in the double bond that already has more hydrogen atoms. What do we mean by that? So if we look at these 2 carbons that are involved in the double bond, which one has the most hydrogens? This one has 2, this one has 1. So the hydrogen atom goes to the carbon within the double bond that already has more hydrogen atoms. So in this case, it would go to this one, right? Because it has 2. And this only has 1. And you can remember this Markovnikov's rule with the phrase, the rich get richer. So this carbon is already rich with 2 hydrogen atoms. It has more hydrogen atoms than the other carbon involved in the double bond. This is the one that's richer. The rich will get richer. The hydrogen will go here, leaving the bromine to go here, okay? The rich get richer. So does everybody understand this concept of Markovnikov's rule and understands how do you decide where does the hydrogen go? Judy, Sasan, do you guys are you guys clear with Markovnikov's rule and the concept of rich and richer?
Yes.
Okay, good. All right. So yeah, you just apply this rule whenever you see that you're doing an addition reaction where you have two not identical. I mean, if they were identical, it doesn't matter. If you have two hydrogens, well, one of them goes here, the other one goes there. No difference. If you have two bromines, well, one of them goes here, one of them goes here. This is the case where you're adding non-identical atoms. So one of them is a hydrogen, one of them is a bromide, and then it matters which carbon which one goes to. And the rule, it's Markovnikov's rule, says the rich get richer. The rich get richer means the hydrogen will always go to the carbon that is richer with hydrogen already. It already has the most hydrogens compared to the other one, and that's where that hydrogen will go. The rich gets richer. Therefore, the product that we would predict would be this one and not this one. This one would not be the correct product of this reaction. All right, I think that that is a very important rule to keep in mind in chemistry. And I think fortunately the phrase rich gets richer is an easy one to remember, and it kind of sticks in your mind. So you just have to remember when this applies. And this applies when you're doing an addition reaction and you're adding something to either a double bond or a triple bond, and they are not identical atoms that you're adding to that double bond or triple bond, then you apply Markovnikov's rule, rich gets richer. Just keep that in mind, guys. Next, we're done with covering our addition reactions. We talked about the 4 types of addition reaction: hydrogenation, halogenation, hydrohalogenation, and hydration. And we talked about Markovnikov's rule. Now we're going to go to substitution reactions. Substitution reactions are reactions where the hydrogen atom is replaced with another atom or group of atoms. And this type of reaction usually involves alkanes or aromatics with halogens to produce organic halides and hydrogen halides. So here we have 2 examples I've shown you. One of them is an alkane substitution. The other one is an aromatic substitution. In the alkane substitution, and one example of an alkane is a molecule like ethane, but it could easily be any of the other alkanes. And here, in this substitution reaction, the hydrogen atom is replaced by another atom, and in this case, it's the bromine. So these kind of switch places, and you get the bromine going here, and this hydrogen comes and binds to this other bromine, and you get this bromoethane, which is a hydrogen halide, and you get this a hydrogen bromide is a hydrogen halide, and then you get this bromo alkane, this bromoethane over here. Similarly, if you have an aromatic ring, and you can have that substitution reaction happening the same way, where you get one of these hydrogens that are not drawn here, but we know are there because we know each one of these points represents a carbon, and carbon is able to bind 4 bonds. So 2 of them are taken up here, 1 of them here, and there's actually a 4th one here going to a hydrogen. So if we keep that in mind, so that hydrogen and this bromine is substituted in, and you get a bromobenzene and a hydrogen bromide. Then another type of reaction is hydrolysis reaction. And in hydrolysis reaction, as you can guess by the title, it involves water. Hydro, the word hydro tells you that there's an involvement of water. And lysis means that something is broken. To lyse something, lysis means to break. When you, in biochemistry or in biology, when you lyse cells, you're breaking cells, and reactions that have the word lysis in them are usually where a molecule is broken. So in this case, in the hydrolysis reaction, you have a covalent bond in a molecule, and it is broken by the addition of water, which is made up of hydrogens and oxygen atoms. So the hydrogen, the H2O is added to this molecule, causing the molecule to break or split into two by the addition of water here. So water, hydrolysis, water is used to lyse, to break this covalent bond and result in two new molecules. And in this type of hydrolysis reaction, you can get two ethanol molecules from this molecule of diethyl ether, or the other name for this is ethoxyethane. And water over here is also a reactant in this, one of the reactants in this. One of them, the one reactant is the diethyl ether, the other reactant is water, and water is added to this bond, causing these bonds to break. So hydrolysis, hydrolysis. And this type of reaction actually occurs in cells in nature, in cells of living organisms when carbohydrates break down. And it is also one way to prepare alcohols. That's a method for alcohol preparation. So that's hydrolysis. Then let's talk about condensation reactions. A condensation reaction is where you of glycogen. So for example, in living organisms, simple sugars like glucose are converted into large storage molecules called glycogen by this type of condensation reaction. And in us, in humans, this glycogen is stored in our liver and in our muscle tissue, where it acts as a storage, and it's just readily available for times where we need that energy for use. Our liver releases it when we need energy, or our muscles release it when we need a sudden burst of energy. We go into our glycogen reserves. So this, I just wanted to show you here that, for example, here is a glycogen molecule, which is a long chain. It's a polymer of all of these smaller glucose molecules bound together. And if we kind of zoom in on this area, we see that we have these sugar molecules that are attached together in these bonds, in these glycosidic bonds. And so when the body joins these molecules together, it does it through hydrolysis, and it does it through condensation. When it breaks, when it wants to break these molecules together, it does it through hydrolysis. So hydrolysis is the breaking of bonds by using water. So if you can see in this reaction, in the scheme that I've shown, the water is being put in. When you have hydrolysis, you're putting it together with this molecule to break this bond and result into these two free glucose molecules. And the reverse, the condensation, you get two glucose molecules, you remove a water molecule from them, and that gives you a new molecule, two glucose molecules that are joined by a glycosidic bond, and this starts the chain of a chain of glycogen. And glycogen is an example of a polymer, which we can talk about in the next lesson, which is actually your independent study unit. This is a very important reaction in living organisms. This is how living organisms build tissue from their food that they consume through their diet, this condensation reaction. Condensation reaction is also important in proteins, in the formation of proteins. So proteins are formed from the condensation reaction between two amino acids. Here in this condensation reaction, again, water is removed and a new bond is formed. In this case, where you're joining two amino acids through the removal of water, the bond that is formed is known as the peptide bond here. Whereas in glycogen, it was referred to as the glycosidic bond here. But they both take place through the reaction, through a condensation reaction where a water molecule, one H, and an OH from each one of these sugars in this case is removed as a condensation of water. And here in protein formation, the two amino acids, one loses a OH group and the other one loses a hydrogen group to produce water, joining them in a peptide bonds. And proteins, as you know, have very important roles in the biological system and help us build very important structures, tissues, enzymes, structural components in our body. They are mostly made from, a lot of them are made from proteins, and proteins are formed through this condensation reaction taking place between amino acid molecules. Condensation reactions also are important in the formation of esters and ethers. So there's many important organic compounds such as esters and ethers that are formed from condensation reaction. Here we have an example of a reaction, a condensation reaction that results in an ester. And you know it's a condensation reaction because you see that a water molecule is lost. So this molecule loses an OH, this molecule loses an H, and a new bond is formed, and a water molecule is lost. If you can think about the meaning of the word condensation, when you have that physical change of water, water vapor from the air condensing on, say, a cold glass, and you get these droplets of water, so it's kind of like water coming out. This type of reaction is also called condensation because you have water coming out. It's a product of this reaction. It's water is removed and it comes out as water. Components of water, the hydrogen and the OH, are removed and you get H2O. So it's a condensation reaction. Ethers are formed the same way. Here you have two molecules of ethanol. One of them will lose an OH, one of them will lose an H, and they will get joined in this ether bond, forming a diethyl ether, and a molecule of water is removed. All right. So did you guys have any questions about, did you guys understand hydrolysis reactions versus condensation reactions? And do you understand how they are reverse of each other? Was that did that concept come across clearly to everybody?
Yep.
Yeah, okay. So if that was clear, then I can go on to the next type of reaction, which is combustion reactions. Combustion reactions, we think of combustion reactions as reactions where an organic molecule is combined with oxygen. It's when things are burning. That's what combustion means. Combustion means burning. So the products of combustion reactions are carbon dioxide and water. So a molecule, an organic molecule is combined with oxygen, resulting in carbon dioxide and water, and also quite a lot of energy. Combustion reactions are highly exothermic. Exothermic is a term, an energy term that means it produces energy, it yields energy, and large amounts of heat or energy are often produced by these types of reactions. That's why when we burn something, you get warmth or you get light, or both in combustion reactions. And we heavily rely on combustion reactions in our daily lives, as we use combustions of many different types of hydrocarbons, such as fossil fuels like coal and gas, to give us lots of large amounts of energy that we use to heat our homes or drive our cars, or lots of other uses. We heavily rely on these fossil fuels because we use them in these combustion reactions to give us yield the energy that we need to live our lives the way we do today. But as you can imagine, as you can already know, that the drawback to burning fossil fuels is that it results in excessive amounts of carbon dioxide. And carbon dioxide is a greenhouse gas, meaning that once it goes into the atmosphere, it traps heat in our atmosphere and leads to smog and global warming, and ultimately to climate change. So that slide covers combustion reactions. Now I want to talk about oxidation and reduction reactions. In oxidation and reduction reactions, you have a change in the number of hydrogens or oxygen atoms that are bound to your carbon, where one reactant is the one being oxidized, while the other reactant is the one that's being reduced. What do we mean by that? In organic chemistry, oxidation and reduction are terms with very specific meanings, very specific definitions. Oxidation is defined as where you have a reaction where carbon forms more bonds to an oxygen and less bonds to a hydrogen. For example, if you have an oxidation of an alcohol, you get the addition of oxygen to a carbon-oxygen bond, to a CO bond, to give you a carbonyl compound. So the carbon forms more bonds to the oxygen. That's oxidation. Reduction is defined as a reaction where your carbon forms fewer bonds to oxygen and more bonds to the hydrogen. For example, you can have reduction of an alkene. Reduction of an alkene adds hydrogen. Remember those reduction reactions that talked about, adds hydrogen to a carbon-carbon double bond to give an alkane. If you remember the halogenation reactions that we talked about earlier on in our lesson today. And so here you have more bonds to hydrogen. So you get a reduction. So these terms are very important. Historically speaking, reactions in which oxygen is a reactant were referred to as oxidation reactions because oxygen was the one that was being was the reactant. And the word reduction usually refers to where you have an addition of hydrogen or a removal of oxygen from a molecule. But now, with our more advanced knowledge of organic chemistry, these terms of oxidation and reduction have come to have broader meanings, and ultimately reactions in which a substance is losing electrons. So now we talk about oxidation and reduction in terms of losing or gaining of electrons. So where a substance is losing electrons, those are oxidation reactions, and reactions in which a substance is gaining electrons are reduction reactions. And in chemistry, these reactions, we will talk about these types of reactions in our later unit. And we will talk in more detail about Leo, the lion, says GER, or another acronym to use is oil rig. And this is just something that helps us remember that loss of electrons is oxidation, gain of electrons is reduction. So loss of electrons, oxidation, gain of electrons, reduction. Same with oil rig. So whichever one is easier for you to remember, either Leo says GER or oil rig. Oxidation is loss, reduction is gain. And we're talking electrons here. Okay. So here, let's continue talking about our oxidation and reduction reactions. So alcohols have a very central role in organic chemistry, and they can be prepared from many other kinds of compounds, such as alkenes and alkyl halides. They can be prepared from ketones or aldehydes and esters and many other compounds. And they can be transformed, again, also they can be made from a variety of compounds, but they can also be transformed into a wide variety of compounds. For example, alcohols can be prepared by the hydration of alkenes. So here, I've on one side, I've described the oxidation of alcohols, oxidation of alcohols to carbonyl compounds. And on the other side, I've described the reduction of carbonyl compounds to alcohols. And I've really gone through it in a methodical way so that you could see really the difference between oxidation and reduction steps. So the oxidation of alcohols to carbonyl compounds is actually one of the most valuable reactions of alcohols, is this type of oxidation reaction of alcohols yields carbonyl compounds. And this is the opposite of the reduction reaction of carbonyl compounds to give alcohols. So when you have a primary alcohol, so here we have a primary alcohol, and if you remember from our previous earlier lecture, we talked about primary alcohols are alcohols where the carbon that the alcohol is bound, the OH group, the hydroxy group is bound to, is only bound to one other carbon group. So in this case, this is that carbon and it's bound to one other carbon. This R is the rest of the hydrocarbon chain. So this makes this a primary alcohol, if you remember. And then if you remember, then the secondary and tertiary alcohols is where the carbon that has that hydroxy group on it is bound to two other carbons. So here are the two other R groups, which are hydrocarbon chains. And then in tertiary, that carbon bearing the hydroxy group is bound to three other carbons. So primary alcohol, secondary alcohol, and tertiary alcohol. We just did a review of what does it mean, primary, secondary, and tertiary alcohol. So when you have a primary alcohol and it is mildly oxidized, an aldehyde is produced. So here we have our primary alcohol. It goes through oxidation and it results in an aldehyde. So an oxidation, you see carbon makes more bonds to the oxygen. And a hydrogen is lost, okay? And if that aldehyde is then further oxidized, it results in the formation of a carboxylic acid. So again, another oxygen group is added here and you get a carboxylic acid. Secondary alcohols are oxidized to produce ketones. And here in this bracket, this square bracket that has the O, this O is described as the oxidizing agent. That's what's carrying out the oxidation process. So secondary alcohols give ketones. Tertiary alcohols, there's no reaction, actually. They don't normally react with oxidizing reactions. So primary alcohols produce an aldehyde, and then if they're further oxidized, carboxylic acid. Secondary alcohols produce a ketone, and tertiary alcohols don't participate in, they don't react with oxidizing agents. So then now we can look at, the opposite of this, which is the reduction of carbonyl compounds to alcohol. So the most general method for making alcohols in the lab and also in living organisms is through the reduction of the carbonyl compound to produce an alcohol. So a reduction of a carbonyl compound adds an H to a C double bond O to give an alcohol. So if you can see in this figure, you have this, this carbonyl group, and it is reduced. This aldehyde is reduced to give an alcohol, a primary alcohol, where H is the reducing agent. And all kinds of carbonyl compounds can be reduced in this way, including aldehydes and ketones. So aldehydes are reduced to give primary alcohols, and ketones are reduced to give secondary alcohols, kind of the reverse of what was happening here, where secondary alcohols were oxidized to give ketones, primary alcohols were oxidized to give aldehydes. This is the reverse. Aldehydes are reduced to give primary alcohols. Ketones are reduced to give secondary alcohols, where this H is the reducing reaction. You can also have the reduction of this carboxylic acid and esters, either a carboxylic acid or esters. You can reduce them to produce alcohols, primary alcohols. So here you can see that hydrogens are added and you get a primary alcohol, the same in this reaction. Esters or carboxylic acids are reduced to give primary alcohol. So here we've described two sets of very important reactions, oxidations and reduction reactions that take place either with alcohol as a reactant, or they produce alcohol. So they can be used as a method of preparing alcohols, or alcohol can be used as your reactant to prepare other molecules such as aldehydes, ketones, and carboxylic acid. Or you can take those aldehydes, ketones, carboxylic acids, and esters to then through a reducing agent, produce primary alcohols. So In summary, of these reactions of functional groups. So we have reactions of alkenes and alkynes, where you have double bonds or triple bonds allow for addition reactions. So you can have the addition of a hydrogen and a hydroxide from a water molecule. That is called a hydration reaction. That's one type of addition reaction. You could have the addition of a H and another halogen. Here X is referred to as a halogen. So the halogens are things like chlorine, bromine, fluorine. And this is the hydrohalogenation reaction. Or you could have the addition of two halogen atoms. So X2, where X is halogen. So things like bromide, chloride, fluoride gases, where those can get added to double bonds or triple bonds. Or you could have a hydrogen molecule, H2, added to double bonds or triple bonds of alkenes and alkynes, and that would be a hydrogenation reaction. So this is a summary of the 4 types of addition reaction that we discussed. And if one or more reactants in this addition reaction are symmetrical, only one product is possible. If both reactants are asymmetrical, then more than one product is possible, and the products are isomers of each other. We also talked about Markovnikov's rules, where you have a halide atom or a hydroxide group in an addition reaction usually gets added to the more substituted carbon atom, and the carbon atom that is bound to the largest number of hydrogen atoms gets the hydrogen, the rich gets richer. And finally, since alkynes have triple bonds, then you can have 2 addition reactions that can take place in a row, one after the other. They can take place in series. So the reactions of aromatic compounds, if you remember, benzene's stable ring usually does not accept the addition of other atoms, but aromatic compounds do undergo substitution reactions where a hydrogen atom or a functional group is replaced by a different functional group. And then we talked about reactions of alcohols, where you can have substitution, so you can have elimination or dehydration, you can have oxidation. And substitution takes place when alcohol reacts with a halogen acid, such as HCl, HBr, or HI. These are all halogens. Hydrogen chloride, hydrogen bromide, hydrogen iodide, hydrogen fluoride. And you can have elimination occurs when the alcohol is heated with a strong acid and a dehydrating agent such as sulfuric acid. You could have reactions of alcohol where you get oxidation of an alcohol to give aldehyde or ketone. We discussed that a couple of slides ago. And then the aldehyde can then be further oxidized to a carboxylic acid. And then those reactions of aldehydes and ketones that we discussed a couple of slides ago, the oxidation of aldehyde produces carboxylic acids, and then ketones don't undergo oxidation. They do not have hydrogen atoms available to be removed, if you keep that in mind. And then you get reduction of aldehydes, give rise to primary alcohols, and the reduction of ketones produces secondary alcohols. So you can look at, you can review those concepts here on this oxidation reduction slide. And Yeah, the one before that too, but mostly here you can see those reactions in detail. And then there was reactions of carboxylic acid. So if you have carboxylic acid, and these are actually these reactions of carboxylic acid, they are condensation reactions, they're dehydration reactions because water is produced. You can have carboxylic acid and a base. So the reaction of an acid and a base, I think you probably learned this in grade 11 chemistry, produces a salt and water. This is a neutralization reaction. If you have carboxylic acid and you react that with an alcohol, that gives rise to an ester and a water. This is an esterification reaction. Esterification reactions are condensation, dehydration type of reactions where water is, a molecule of water is lost. And then reactions of esters and amides. Hydrolysis of ester or amide cleaves the molecule into two. So hydrolysis, if you recall, just looking at and understanding what the name means, hydro means water, lysis means breaking up. So using a molecule of water to break another molecule. So an ester plus water, this is a hydrolysis of an ester, will result in carboxylic acid and an alcohol. So cleaves the molecule into two products. And here again, water is used to cleave an amide into a carboxylic acid and an amine. So here it's the hydrolysis of an amide to produce a carboxylic acid and amine. This and hydrolysis can take place in both an acidic and a basic environment. It can take place in either one. And usually hydrolysis requires heat. So when you are setting up these are reactions that have to be heated in order to take place. They require an input of energy. Okay. And then I have this table here just to be able to sort of think about and conceptualize how all of these reactions are reverses of each other and how one leads to the other. For example, alcohols can be oxidized to give carboxylic acids. Carboxylic acids can be go through a condensation reaction to produce esters. Esters can go through hydrolysis to produce carboxylic acid and an alcohol. So there's all of these relationships and all of these reactions. You can have addition reaction of hydrogen halide or a halogen itself to an alkene or alkyne, and that will give an alkyl halide, or you could have an elimination from an alkyl halide and an elimination of a hydrogen halide or a halogen molecule to give an alkene or an alkyne. Alkenes and alkynes can then further be reduced to alkane molecules, having lost their double bond. You could have addition of water to produce alcohol in these to these alkenes and alkynes, or you can have the elimination of water to give from alcohols to give alkenes or alkynes. So yeah, you can explore some of the relationships here to understand how they're related. This is really nothing for you that you need to memorize or learn. This was just more to see the concept of how these organic reactions all kind of tie in together, and you could take them one way or the other way, depending on your conditions, and you could produce something or use it to produce something else. So then I have just a few support questions for you guys to practice with. And then finally, key questions. So this week you have 2 sets of key questions due on Sunday. You have key questions from lesson 6 and key questions from lesson 7. So key questions 6 and 7 are both due this Sunday. And now Monday is Thanksgiving. We don't have a lesson on Monday. On Wednesday, we will review. We will do a review session. So let me just, let me share. What am I going to share with you? This one. Okay, so I just want to do, show you that. Okay, so this is where we are today. Today was Wednesday, October the 6th. We covered lesson 6, which was types of organic reactions. So on Sunday, October 10th, this Sunday, both of these key questions, 6 and 7, are due. Then our next lesson on polymers, this is an independent study unit, guys, which means that you guys can study this on your own. I will provide you with the slides that you can look at and study. And then on Wednesday, so we don't have any class on Monday, it's Thanksgiving, but on Wednesday, I will do a unit 2 review. In my unit 2 review, I will, time permitting, also cover polymers. I will go over that again with you guys, but it's mainly an independent study unit. It's a very short section that I encourage you to read up on your own, because you do still are expected to know this. And then the key questions for lesson 8, if you choose to do them, you don't have to submit, you don't have to hand in key question of number 8. But if you do choose to, they are due Sunday, October 17th. So next week, we only have one thing due, and even that one thing is a bonus. I encourage you to do these bonus questions if you can, because it will help you at the end to raise your marks. So at the end, for however many additional bonus questions you've handed in, I will look and I will drop that many of your lowest marks in your assignment. So that gives you a chance to improve your marks. Okay, so the other thing that I would like to do next week, next Wednesday in our unit review, is that I didn't get any of the periodic table diagnostic sheets back from anybody. And I would really like to get a feel for what is your understanding, and just want to get a feel for how is everybody, what level is your understanding of the periodic table. So now that you didn't, it's not for marks, it's just more for my benefit and also your benefit, for me to understand how much you guys know, what knowledge might be lacking, what gaps I need to fill in. So next Wednesday during our unit review, if you could bring with you, if you could have in front of you during the review, your completed sheet of the periodic table diagnostic. And that sheet is posted on, I've shared it with you on your shared with me part of your Google Drive. And I think I may have also emailed it to you guys early on, but anyway, you can definitely access it through your Google Drive. If you could complete that, just so that you yourself have a sense of what are gaps in your knowledge as with regards to the periodic table. And then when we are doing our unit 2 review, I would also like to go over that periodic table diagnostic. And I'm going to ask you guys to tell me what do you think is the right answer there. And then we can go through it and we can troubleshoot and figure out if everybody knows what the right answer is, or if we can work on it a little bit more so that we have a better understanding of how to utilize all the information that's available to us on this periodic table. Okay, so any questions about what I just talked about what we're doing next Wednesday, about the independent study unit, about the idea of handing in bonus key questions? Does anybody have any questions with regards to any of that? Are we all clear?
No question.
No questions. Okay. So Judy, you're all good too. Okay. So, all right. So in that case, let me go back to our lesson, what I was sharing with you. All right. So any part that anybody felt wasn't clear, and maybe we can go over again. We have got like a good chunk of time still left in our lesson. So we can start from the top again, or if you guys have been working on some of your other lessons and reviewing those, if you can tell me if you have any questions from previous lessons, lesson 5, lesson 6, I can also open up those lessons and we can go over those and review anything that you guys didn't understand. So any questions? So we talked about the types of organic reactions, addition reactions, and then we talked about there's 4 types of addition reactions, and we went through these 4 in detail. We went through hydrogenation reaction, where you have the addition of H2, hydrogen gas, an H2 molecule. Addition reactions take place with alkenes or alkynes. So these are with unsaturated hydrocarbons that have either a double bond or a triple bond. Right? Remember, addition reactions take place with unsaturated carbons that have either double bonds or triple bonds. Okay. And then there was the 4 types. There was the hydrogenation. There was the halogenation. So that was with a molecule of bromine or chlorine or fluorine or iodine. So these are all the halogen molecules on the periodic table. And these are then added to an unsaturated hydrocarbon, a hydrocarbon with either a double bond or a triple bond. And there's no leftover atoms. There's added straight in. So the double bond is broken and the resulting bonds are then occupied with the bromine atoms, with the halogen atoms, if you may. And that these halogenation reaction can also happen with aromatic hydrocarbons. Aromatic hydrocarbons, again, have to have an unsaturated component on them. They have to have a double bond. So you could have a bromine being added to this to give a dibromo cyclohexane. And then we talked about hydrohalogenation reactions. Same idea, except instead of either H2 or Br2, you can add a hydrogen halide, which has 1 hydrogen and then a halogen atom as well. So we talked about that one. And we talked about the 4th type of addition reaction, which is a hydration reaction, that you can add a molecule of water in this type of addition reaction to a propene to give rise to alcohol. And then our big question was, which product are you going to have? Where is the hydrogen going to go? Where is the OH going to go? Where is the hydrogen going to go? Where is the bromine going to go? Where's the halide going to go? Which one of these is correct? Is the correct product? Which one of these is the correct product? And then I talked to you about Markovnikov's rule, and the rule of rich gets richer. The hydrogen atom always goes to the carbon atom within the double bond that already has more hydrogen atoms. The rich gets richer. Then we talked about substitution reactions. We talked about hydrolysis reactions. We discussed how a hydrolysis, what does hydrolysis mean? Well, if you break it up, the word hydrolysis means hydro, water, lysis, breaking. So in hydrolysis reactions, a covalent bond is broken by the addition of a water, by the elements of water, the hydrogen and the oxygen. And H2O is then added to the molecule, causing the molecule to split into two. So here you have the hydrolysis reaction of an ether, and this water molecule breaks this bond, and the components, the hydrogen and the OH, are added, and resulting in 2 molecules of ethanol here, for example. Then we talked about condensation reactions and how they were important in the formation of glycogen and also protein. And I talked to you about how condensation reactions are opposite of hydrolysis reactions, where in hydrolysis reaction, water is used to break a bond and give rise to 2 products. In condensation reaction, it's the reverse. 2 products are added and a molecule of water is removed, it's condensed, and you get a product where the 2 original molecules are now joined together in a bond. In the case of glycogen, you have the joining of 2 glucose molecules together in a condensation reaction. The water molecule components, the H and the OH, are lost, and you get the formation of this glycosidic bond. In the case of proteins, the condensation reaction takes place between 2 amino acid molecules. And amino acids are the building blocks of proteins. So when you get a condensation reaction between 2 amino acid molecules and the components of water, the OH and the H, are lost, you get a condensation, and the 2 amino acids are now joined together, and a new bond is formed, and this bond is called the peptide bond. And this is a very important bond. If you go on further to study proteins, you will understand more about the importance of the peptide bond and the condensation reaction. We talked a little bit more about the formation of esters and ethers through condensation reaction. Again, you have a molecule of water being lost and a bond formed to produce a new molecule, which is made from joining of these 2 reactant molecules. In this case, the ester is formed from an alcohol and a carboxylic acid. It's formed by a methanol and a butanoic acid. Water is removed and you get methyl butanoate, which is an ester. You can form ethers through condensation reactions. In this case, you can have 2 molecules of ethanol, and through the condensation reactions, the components of the atoms of water, the OH and the H, are condensed and removed, and the 2 are joined in an ether bond. Okay, we quickly touched on I'll review again. We quickly touch on combustion reactions. Combustion reactions, I think we're all very familiar with. It's where something is burning, where you're using oxygen. And in a complete combustion reaction, the only products that remain is carbon dioxide and water. And both of these are in the form of in the gas state, so carbon dioxide gas, and water in the gaseous state, which is also known as water vapor. So water vapor and carbon dioxide gas, and lots of energy, and this is the same reaction that takes place within our cells when we go through the process of cellular respiration. We convert the nutrients, the sugars, for example. Here's a molecule of sugar that we consume. We go through the process of cellular respiration, and we combine it with oxygen, and we convert the nutrients into cellular energy of ATP, and also into carbon dioxide, which we exhale, and water vapor. And this is also the reaction that we use in fossil fuels. When we burn our fossil fuels to run our automobiles, to heat our homes, to run our factories. And unfortunately, the carbon dioxide that's produced from this is a greenhouse gas. It traps heat and leads to global warming. We talked about oxidation and reduction reactions, and where one component is oxidized while the other one is reduced. And we talked about the acronym LEO says GER, or oil rig. And this helps us remember that when you're losing electrons, that's an oxidation reaction. When you're gaining electrons, it's a reduction reaction. Oxidation is loss of electrons, reduction is gain of electrons. And these will be discussed in greater detail in another unit. But for now, what's important to remember is that oxidation is also where you have carbon bonds forming, carbons forming more bonds to the oxygen, where in reduction, your carbon is forming fewer bonds to the oxygen, and vice versa, making more bonds to a hydrogen and less bonds to a hydrogen during an oxidation. So in this slide, I'm not going to go over it in great detail, but I'm just going to quickly touch upon how these reactions are reactions that either alcohols are oxidized to produce carbonyl compounds, or carbonyl compounds are reduced to produce alcohols. So here you can see how oxidation reactions are opposites, where the oxidation of alcohol to carbonyl compounds and is the opposite of the reduction of carbonyl compounds to give alcohols. And you can get primary alcohols in oxidation with the use of an oxidizing agent to produce an aldehyde and then further oxidize to a carboxylic acid. Or you could have your carboxylic acid reduced to a primary alcohol. You could have your primary alcohol oxidized to the aldehyde, or you could have your aldehyde reduced to a primary alcohol. You can have your secondary alcohol oxidized to a ketone, or you could have your ketone oxidized to a secondary alcohol. You could have your carboxylic acid reduced to a primary alcohol, or you could have your ester reduced to a primary alcohol. Both of these is possible. And and tertiary alcohols, there's no oxidation reaction. And then I had some summary slides. And then finally, the key questions that are due this Sunday, together with key questions from lesson 6. All right. I'm happy to answer any questions, either today's lesson or the previous other 2 lessons in Unit 2. If anybody has any questions, you can please ask them now. Otherwise, I'll see you next Wednesday. So remind you again one more time, there is no class on Monday. Monday is Thanksgiving. No lesson on Monday, but I'll see you on Wednesday, where we will go through Unit 2 review. Okay. And also, if you could bring along your completed periodic tables with you, because I'll be asking you questions and we can discuss our periodic table diagnostic. Okay. All right, everybody. I wish you all a very good evening.
Thank you. Have a good night.
Thank you. You
Thank you.
too.
Bye.
Bye-bye.
Goodbye.